Well, good afternoon, everybody. I hope you had a good lunch, and I'm very happy to be here. So I'd like to start off by thanking Mike Cotton for inviting me to give this talk. The talk, we're going to spend a half hour talking about radar clutter. And of course, this is a topic that's very important to the radar community, and a lot of time and effort has been spent on characterizing clutter and developing approaches to mitigate the impact of clutter on radar performance. So to start off, this was kind of one of the emails passed between myself and Mike, and he asked me to talk about radar clutter. And, this should be contrasted to clutter from the perspective of one-way propagation for radio communications, and also talk about some of the approaches that we use in the radar community to mitigate the impacts of clutter on detection performance. So that's where we're going to focus. I'll talk about radar clutter characteristics and clutter modeling, and some of the preeminent techniques, or a preeminent technique for removing clutter from impeding detection performance. I only have a half hour to maximize the amount of damage I can do. So for that reason, I'm going to focus on aerospace radar, so airborne and spaceborne radar applications, because that's really the most challenging from the perspective of clutter mitigation. And we can consider surface systems usually as a special case where platform height and velocity go to zero. So with that all in mind, these are kind of the topics. I'll make some introductory comments, and then we'll talk about the characteristics of Doppler spread clutter from the airborne or spaceborne radar perspective. And then I'll talk about detection processing and some key metrics that are central to characterizing the goodness of the radar design and the different algorithms that are used to provide acceptable detection performance. And I'll finish by just giving you some highlights about a technique called space-time adaptive processing, which is really a central element of modern radar design. So to start off, I'll just make some basic comments. So first of all, in the radar world, we really strive to achieve noise-limited detection performance. And I know that's probably very peculiar to the communications community, but the reason why is we want to maximize the volume coverage and the detection ranges that the radar can provide. And so because that's sort of a basic philosophy, radar system designers go to great extents to try to approach that noise limited bound. And so radar systems use very complex designs to mitigate radio frequency interference and clutter. And so the primary focus then becomes maximizing output signal to interference plus noise ratio. And the way this is done is by exploiting radar degrees of freedom as a central tenet. These degrees of freedom include spatial frequency, polarization, fast and slow time, and pass-to-pass or multi-pass processing, as well as varying waveform attributes and developing some sophisticated approaches to resource management. But the ultimate goal is that, while SINR can never exceed signal-to-noise ratio, when you add clutter or interference, you can never get better performance. The goal always is to approach that noise-limited bound. The other thing I'll say, there's an adage in radar, and that adage is that one person's clutter is another person's target. So it turns out that clutter and target signals have very similar characteristics. So to motivate this discussion, we'll talk about the challenges of Doppler spread clutter, and I'll go through what I mean by that in a moment. Doppler spread clutter naturally impedes target detection because there are angles where clutter comes back into the radar with the same Doppler frequency as the target of interest. So if you're not familiar with radar, this is kind of my pretty picture summarizing the basics of a radar course that would take a few days and just a few minutes. So the basic idea is that the radar actively interrogates the scene of interest and generates different radar products. There's three primary radar products, and Typically, the radar will send out a series of pulses to illuminate the scene, and this is done so that we can isolate the transmit function from the receive function and still get a range measurement. And then the radar will collect thousands and thousands of voltages from a particular range bin of interest, a particular distance from the radar, and will use sophisticated algorithms to generate the radar products, which include, as examples, images like I'm showing here on the bottom of the slide, which are estimates of the electromagnetic backscatter from a fixed scene. Or the radar will strive to generate indications of moving targets. Or a third primary mode is to decide whether or not something has changed in the scene from a prior pass. That's called change detection. And advanced radar systems may have 30 different modes, but the three basic products are moving target indications, radar images, or change metrics, change detection metrics. For the purpose of this discussion, we're going to focus on moving target indication. That'll primarily motivate our discussion around clutter, since clutter is a mortal foe of good moving target indication. Again, and just from a big picture perspective, radar signal processing for moving target indication follows this basic flow. So we typically start in modern radar systems with multi-channel antennas. So the words channel or subarray or element are usually synonymous in radar lingo. And each of these spatial channels has its own receiver. And then we'll collect data over these multiple pulses, like I mentioned. And the typical processing then will first strive to remove radio frequency interference, so noise jamming or deceptive jamming. And then the next stage will typically try to suppress clutter. Sometimes you can, depending on the source of interference, combine these two stages. But what I'm really trying to show here is that we take these thousands of voltages, and through processing, we squeeze them down to a single complex voltage, which ends up being a pixel in the range Doppler map. So the range Doppler map is a primary radar product, and we make all of our decisions from these range Doppler maps. In this particular case, this single pixel, our goal is to decide whether or not a target is present at that particular range and that particular Doppler for a given steered angle for the antenna. And so because these returns are stochastic, the pixels themselves have probability distributions. And so in radar nomenclature, the one distribution corresponds with the null hypothesis, which is the case of target absence. The other case is the alternative hypothesis, where the target is present. And in this simple illustration I'm showing here, you can see that necessarily the two distributions overlap. And so there's ambiguity in the decision-making process. So we set a threshold, like I'm showing with this orange line, and anything that crosses the threshold is declared to be a target. And so hopefully we're right more times than we're wrong, and we can't tolerate a high false alarm rate. And so the best scenario, of course, is through processing to maximize the separation between these two distributions. And so we do that through radar design, through signal processing, and through the selection of the appropriate degrees of freedom. Everything that I just described is rolled up in the receiver operating characteristic that I'm showing here. So I'm plotting this as output signal to interference plus noise ratio, which is after integrating all of those voltages together. This is probability of detection on the y-axis for different probabilities of false alarm. So it's typical in radar to make usually except one error in a million decisions. And as a benchmark, we usually want probability of detections around 90%, which requires on the order of 13 dB output SINR. You'll notice from the ROC curves that small errors in or small degradation in SINR will lead to big changes in probability of detection. So the goal of processing is to be as high up on this ROC curve as possible. And of course, clutter impedes output SINR. And so on this chart, I'm giving you sort of a bird's eye view of how clutter manifests in an airborne or spaceborne radar. So in this particular case, the green boxes correspond to a single range bin of interest. And what happens is that the platform flies and illuminates the scene of interest. Each of these cells are illuminated and return a response back to the radar. And the different boxes are at different angles with respect to the array normal. Each of the different points also has its own Doppler. Small changes in angle lead to small changes in Doppler. And the Doppler frequency is the projection of the velocity vector of the platform onto the fixed scene. So it turns out that main lobe clutter will mask slow moving targets, but side lobe clutter is also an issue because even though it's at a different angle in Doppler than the target of interest, sometimes we look for weak targets and that clutter signal can be strong enough to impede detection. So stationary clutter is coupled in angle and Doppler, and if we look at each of these points here, they'll map in the angle Doppler space to points along this line that I'm showing right here. So small changes in angle lead to small changes in Doppler, and knowledge of angle is sufficient to tell us the Doppler of that fixed point on the Earth's surface. Moving targets, however, don't follow that same rule. So the angle of arrival for the target and its Doppler are independent. For example, it depends on the motion of the target and how hard somebody is pressing the accelerator. So you can imagine that in signal processing, one of the goals will be to separate the returns out based on their angle Doppler responses. So I'm going to talk a little bit about the processing now. So as I mentioned, we have these thousands of voltages for each range bin, and we can conceptualize them using the radar data cube. So receiving data across a multi-channel array will fill up this cube with, for each range bin, M channels worth of data over N pulses. And then, of course, this is the range dimension. And for the type of processing I'm talking about, we'll take each slice of this cube, which we call the space-time data matrix, and we'll process that, interrogate that, looking for targets. Now, it's inconvenient to process a matrix, so we'll stack each column one beneath the other, and we'll end up with something known as the space-time snapshot, where each of these colored blocks corresponds to the spatial channel collection for a given pulse. So the goal of processing and getting that pixel in the range Doppler map, like I just described, involves weighting each of the voltages in this vector of length mn and taking the inner product of this weight vector with the data to get a complex scalar. And different weightings will give different performance. But for a second, you might ask, well, what would a single point scatter look like in this data cube? And so the response of a pulse Doppler array to a unit amplitude signal with a given direction of arrival and Doppler is described by what we call the space-time steering vector. And so because we've taken the data and organized multidimensional data into a vector, that suggests the use of a tensor product. In this case, this notation means the Kronecker product, which just involves stacking the data just like the way I showed on the prior chart. So this term right here, this vector is of length m, and it's known as the spatial steering vector. It describes the linear phase progression across the spatial channels for a propagating wave coming from a particular direction of arrival, nominally denoted by this variable gamma sub s. This vector right here is of length n, and it's known as the temporal or Doppler steering vector, and it describes the phase progression from pulse to pulse due to the radial motion of the target relative to the radar. And so the stacking of these two vectors together gives us this response here, which is known as, I already said, the space-time signal vector. And this is a really important expression, especially considering clutter, because in the case of clutter, once we choose, say, angle, Doppler's automatically calculated. And so an ensemble of these weighted space-time steering vectors is how we model the clutter response. We also use this same model or this same term with a complex scaling to model the target return. So the target return looks like a scaled version of the space-time steering vector, but Doppler and angle are independent. The two-dimensional Fourier transform of the space-time signal vector gives us a two-dimensional sine x over x response, a sync response like I'm showing here. And so again, if, for example, this was a moving target, it would show up at a corresponding Doppler and angle. But clutter, as I'm going to show you on the next slide, looks like an ensemble of weighted space-time signal vectors. So using that description on the prior slide, I'll start by just showing you what clutter would look like in the angle Doppler space for a given range bin. So, so here you can see the clutter response extends along this ridge for a side-looking radar. I'm also showing white noise jamming here, which is correlated in angle but uncorrelated in Doppler. And then I'm showing a moving target that falls off of the clutter ridge. So you can imagine a filtering strategy would be to maximize the gain on the target while driving a null along the clutter ridge and the jamming. If we were to project the target into any one-dimensional space, either the angle domain or the Doppler domain, you can see that the target would be masked by the interference. The way that distributed clutter is modeled is then given by this expression right here. So this is a length NM vector for range bin K. And what we do is we take over-resolved pixels on the Earth's surface, usually at about a quarter of a resolution cell, and we calculate all of the factors that determine the signal return from that patch and use that to weight the space-time steering vector. And then we sum up n sub c patches over n sub a range ambiguities and sum all that up. We can also, you know, and this is very important for radar design and performance characterization, model the clutter covariance matrix. So if we assume each of the patches is statistically independent, the clutter covariance matrix ends up being given by the outer product of the space-time steering vectors weighted by the power sigma squared for that patch, again, summed up over n sub c patches and n sub a ambiguities. The Fourier transform of the two-dimensional Fourier transform of the covariance matrix is the power spectral density that I'm showing here. So this picture and this expression are Fourier transform pairs. And that's important because the covariance matrix, if we can get the null hypothesis covariance matrix, that's everything we need to know to characterize the clutter and interference environment. And that becomes a central element of a signal processing solution to suppress or mitigate the clutter impacts on detection performance. So these pretty plots right here are examples of super resolution spectrum for airborne radar in a side-looking configuration and a forward-looking configuration. So a side-looking configuration is consistent with a surveillance radar, and you can see clutter falls along this peaked ridge right here. So typically the radar will look for targets in the direction it transmits, so in this direction. And so side lobe clutter here can mask a target at this particular Doppler. In ground moving target indication, we're actually looking for targets very, very close to what would be called main lobe clutter in this region here or here. So this line here ends up being a stripe in the range Doppler map. This example here is for a forward-looking radar, for example, in the nose cone of an aircraft. And in this case, clutter falls along a circle, and all things equal, looking for a target, say, in the transmit direction. So in this direction here, clutter is twice as hard to remove because we have to cancel clutter at both angles for a given Doppler. So forward-looking arrays have left-right ambiguity, and so clutter comes in at these symmetric angles in the same Doppler. But you could imagine a good solution would be to build a filter that dynamically adjusts its response and drives a null along these points here or these points here to reduce the impact of clutter on radar target detection. These plots here just show the goodness of the model that I just showed. I took data from this 24-channel L-band radar test bed. You can see the antenna is port mounted right here. It's held up by these big radome struts you can't see in the radome. And what I did is I took training data from these 100 range bins here or these 100 range bins here, and I plotted out this super resolution response. You can see the clutter in this S-shaped response in angle Doppler. And this plot right here is what I simulated using the model I just showed you. So it's a very good match. The primary difference, of course, is all this stuff here, we'll call it stuff, and that's a result of multipath from the radome struts. So I sort of refused to model that because we wouldn't build a fielded radar mounted this way. We would belly mount the radar, put it on top of the aircraft to avoid that end fire coupling. So that wouldn't be an operational effect. But overall, these are pleasing pictures because they show how closely we can match simulation with real data. Of course, to do this, I had to have navigation data, and this system has an inertial navigation system strapped behind the array. Okay, so the radar community spent decades collecting clutter reflectivity data, and I don't want to bore you with those details. I'm just going to make a few points before I move on to the next slide. And just a few observations. So in the radar community, it's very common to use something called the constant gamma model. So we take gamma, which is a reflectivity. It gets a little confusing because we call a number of things reflectivity, but we take this value gamma and we multiply it by the sine of the grazing angle, which is the angle that subtends the tangent to the Earth's surface and the radar line of sight. And so this is actually what data would look like, collected data, and it may be a little challenging to see, but at very low grazing angle, there's very little backscatter. There's more forward scatter, but eventually we get to a grazing angle where we get increasing backscatter, and this follows that sine of the grazing angle response right here. So the constant gamma model is good to about 60 degrees or so, depending on the type of clutter. This plot is for grass at C-band, and this region here is the specular region. So the second point I'll make is that the clutter scattering is a result of the roughness of the surface relative to the wavelength. So for grass, you can see that at L-band, the wavelength is very long, much bigger than a blade of grass, and the backscatter is much lower. But as we go up in frequency, the backscatter becomes greater and greater for grass. Trees are more complicated, so you get more backscatter over a range of grazing angles and very little frequency dependence because the trees are bigger than the wavelengths that we typically interrogate them with. So you'll notice this weird point here at L-band. That's probably a result of the fact that L-band does propagate through foliage, and so energy is probably escaping through the trees and getting trapped under the tree line at that particular grazing angle. And then this is an example for wet snow, which you can see it's less backscatter, but you can see at shorter wavelengths the surface is rougher, and we get more of a return from the wet snow. You can use information like this, and you can combine it with cultural databases to get results like this. So what I'm showing you here is measured foliage penetrating radar data. This is UHF radar data from an airborne radar, and then this is what we simulate. And so you can see it's a remarkably good match. There's some differences, like we used MATLAB and double precision arithmetic, and the radar, of course, has limited dynamic range. And you can see there's a little bit, this must be low tide. This result doesn't fully show here. But otherwise, there's a lot about the clutter environment and the returns that are predictable with good navigation systems and well-calibrated radars. Okay, we're on the home stretch, so now I'm going to just talk about how we characterize the impact of clutter on detection performance. So this is a generic radar detection processing architecture. And all things equal, the critical step here is clutter and RFI filtering, so removing clutter so that we maximize SINR here. Typical radar systems frequency hop the radar from coherent dwell to coherent dwell to deal with target fading. So roughly at this point, we need about 9 to 10 dB of input SINR if we're going to combine 4 frequency hop coherent dwells to get a detection probability of 90% at a false alarm rate of 1 in a million. So the moral of the story is SINR is very important, and our goal is to maximize output SINR. And there's all different approaches we can take to try to mitigate clutter. And so for this reason, radar engineers embrace this metric called SINR loss, which can get kind of confusing. It's a little wonky. These are numerator terms. And so, as I mentioned earlier, we also embrace the idea of trying to achieve noise-limited performance. So output SINR is the product of, for a given angle and Doppler, is the product of signal to noise ratio calculated through the radar range equation and typical link budgeting times loss factors. And you can have as many loss factors as you want. But what's typical is to use what we call clairvoyant SINR loss, which is the ratio of output SINR when we know everything about the signal processing implementation that's needed, divided by signal to noise ratio. And this term is influenced by the radar design, the particular choice of clutter mitigation algorithms, as well as the environment itself. And then typically the second term is called adaptive SINR loss, and it's the degradation in performance between the adaptive filter implementation and the clairvoyant case. So I've already suggested the role of the covariance matrix in some of these adaptive filtering implementations, and we don't know that in practice. We have to estimate it. Sometimes we do a good job, sometimes we don't. But the job of the signal processing engineer is to minimize these loss factors. This is an example of clairvoyant SINR loss. So noise limited performance is at 0 dB. Maximum loss is at the heart of clutter. So that loss is about equal to the clutter to noise ratio. Different algorithms will give you different shape curves. And sometimes we use key points like tolerable losses to define radar characteristics like MDV, which is known as minimum detectable velocity. So I'll show you an example of a comparison between adaptive filtering and non-adaptive filtering to illustrate the use of SINR loss in just a second. But this chart's an eyeful, and you know, there will be a test on this after I'm done. Just kidding. I don't even know if everybody's still there. I'm just talking into my computer, so hopefully you're still there. But I don't want to belabor this. I just want to point out that if you went through the exercise of maximizing output SINR, you can form an expression that looks like this quadratic over this quadratic. And you can choose any weighting you want and characterize the performance with SINR loss. The optimal weighting is shown here in the red box. And that optimal weighting is the inverse of the null hypothesis covariance matrix times the space-time steering vector with an arbitrary scalar. So this term here suppresses the colored interference, clutter, and jamming. And then this term here implements a two-dimensional beamformer in angle and Doppler. So this is the weighting we would use to apply to each of the elements of that space-time data vector to combine everything into a scalar as a pixel in the range Doppler map. So just some examples of the goodness of STAP and the goodness of SINR loss. I have two pretty examples here. The first one They're pretty to me, maybe not to you, but I took that Makaron data and I estimated SINR loss for different range bins, 200 to 300, 300 to 400, and so forth. As well as I simulated what I thought the SINR loss should be. So I'm trying to match SINR loss to the near ranges, 200 to 300. And you can see the estimate kind of looks like a least squares fit of the data. It wasn't intended to be that way. But what I learned from doing this is a few things. One, different types of clutter will naturally affect the shapes of the curves. So there's less backscatter from fresh water than over land. So the blue and the green are
He freeze or do we freeze? Oh.
Bill, can you still hear us? Going too smoothly. Since
We lost him. Yeah. I think he's sure he's gonna try and join back in this second.
All right, we're gonna give Bill just a minute or two to try to join back in. In the meantime, you could start working on some questions. Tempted to ask Billy to come to this. You have enough to do now. I got a bad stuff. Oh yeah, that's right.
Coming back in. I think.
Can you hear me? I'm back.
Yes, Bill, we can hear you.
Sorry about that. I don't know what happened. Let me pull the slides back. I'm almost done.
Perfect. All right. We'll let you know when you can see them.
Can you hear me and see the slides?
Yes, we can.
Okay, sorry about that. I don't hotel Wi-Fi. So hopefully, let me get my pointer back. So I had just talked about this SINR loss plot here. Did you hear my comments about that?
I think we heard most of them, yeah.
Okay. So the other one I just want to point out here is SINR loss comparing the non-adaptive solution in purple with the STAP solution in green. So, and then the importance of a long track length in mitigating clutter. So the ideal response would be a bracket, but this is the example of a 0.9 meter array with Fourier only processing. The same data processed using adaptive processing, STAP, is shown in green. So to resolve the clutter with the non-adaptive solution, we'd probably have to increase the array from a size of 0.9 meters to about 9 meters, probably make it 10 times longer so that this main lobe clutter that I'm showing here would squeeze into the response shown here in green. So this is my last slide. So this is just the money chart on STAP. So what I'm showing you here is the clutter power spectral density for a side-looking radar. The clutter falls along this ridge here. We have two noise jammers. The STAP response would show deep nulls on the two jam strobes, as I'm showing here, and a deep null along the clutter response. And that's calculated by taking R inverse S and, of course, calculating the corresponding transfer function. Where here we're pointing the beam at this particular angle and Doppler very near to main lobe clutter. So STAP is a super resolution technique, and that also is what I was showing here because it's model based. It isn't simply just taking a Fourier transform, but using a model of the environment, and that model is the covariance matrix. So to summarize, clutter is returns that are target-like but aren't the target of interest. So we talked about reflections from the Earth's surface as seen by airborne or spaceborne systems. So we call that ground clutter. Ground clutter exhibits coupling in angle and Doppler, whereas moving targets have responses with uncoupled angle and Doppler, and we exploit that in the signal processing to pull the target of interest out of the clutter background. I tried to just highlight that radar systems use some complex mechanisms and approaches to mitigate the impact of clutter on performance. We exploit the radar degrees of freedom. Depending on the source of interference, we would use different degrees of freedom. So for ground clutter, we use the spatial and slow time degrees of freedom. But for other interference problems, we would use different degrees of freedom. And I did suggest that STAP is a super resolution technique, which lets us build reasonable sized antennas and still see slow moving targets or targets impeded by side lobe clutter. And, I know that bandwidth is a big issue here. I'll point out that another approach to finding targets in clutter would be to resolve the target relative to the clutter background, and that usually requires a lot more bandwidth. But if we can cancel the clutter, we don't need the same range resolution. We can go to lower bandwidth and save time and complexity in processing. Finally, I didn't fully suggest this except with the one SINR loss plot with the lobing effects due to moving targets, but ground clutter can be very complicated. And sometimes people say, well, what density function should you use to describe the clutter background? And the answer is, I don't know, because some of the models people have used aren't even, physically realizable. So really clutter is they don't match the laws of physics, I guess I should say. But the real answer is clutter site specific. So we have to deal with spatially varying clutter, clutter discretes, which are usually man-made objects like fences and buildings and telephone poles, as well as dense moving targets. And so we call this variation in clutter heterogeneous clutter, and a lot of time and effort has gone into understanding approaches to make robust radar signal processing chains that operate in these heterogeneous environments. So with that, I'll ask if there are any questions, and I'll do my best to answer them. Hopefully this was useful to your meeting.
Thank you, Bill. I'm scanning the room for the first answer.
Got some on the side.
Hi, Bill.
Okay.
Are there types of signals
Oh,
or
that
types
one.
of signals that could
Sure.
impede
Sure.
or defeat
See what it looks
clutter cancellation algorithms that you're aware of?
I'm having a little bit of trouble hearing you, so could you either yell or grab a microphone?
No.
I'm speaking into a microphone.
Oh, okay, I'll listen carefully. Go ahead.
Are there shapes of signals or types of signals that would interfere or defeat clutter cancellation algorithms?
Well, certainly the way that we implement adaptive filtering is we have to gather estimates from the environment. And so, with radar, we usually focus a lot of research on clutter mitigation. Certainly, there's a lot of work on electronic protection as well. And because of the security issues around radar, those are usually handled as special types of topics. But suffice it to say that mechanisms have to be built in to anticipate allowing the radar to adapt in an appropriate way. And like I was suggesting, there is a lot that we know about the clutter environment. So we can compare the adapted response with what we what we anticipate. We can't do this deterministically and achieve the best performance. But usually the response in angle and Doppler is deterministic. The scattering itself is stochastic.
Question. Thank you, Bill, for this.
And just back to that question, the references give some examples. So part of the answer or part of the information I mentioned would be in the reference, one of the references I gave, reference 12 talks about how to constrain adaptivity using this knowledge-aided parametric approach.
I just couldn't follow everything. It was too fast for me, but just from a qualitative standpoint, I understand that the beams that you're pointing, the radar beams are narrow, and but but you're trying to detect moving targets. So if something is a building that's stationary or something, then isn't it fairly, as long as it's not too close to your target, isn't it fairly easy to define that and remove it based on the fact that doesn't have a Doppler itself? Also, do you ever worry about reflections off your moving target that hit a building and then reflect into you? I guess those might be short-lived, but they have Doppler. So
okay. So in the example you gave, just hopefully this helps. If you imagine a particular range of interest, suppose we're looking at a moving target in the center of the beam, but there's like a large building here. So the building will show up on the clutter, the clutter ridge here, but the target, falls off the ridge. But the response of that building is usually so much stronger than the target that its response would swamp out finding the target. The building, the clutter signal could be 40 to 60 dB stronger than the target of interest, even after integration. So it is really important that we find degrees of freedom where we can separate the clutter response from the target and then mitigate through filtering that clutter signal. And then the other thing you asked is, what about multipath? And so, multipath is always a challenge, but it doesn't impede radar detection except in very complex environments, like in urban environments. And there have been programs that actually take advantage of multipath to localize the target detection. So in radar, a lot of times we use multipath to get height above terrain information, or actually to localize the target on roadways because of building geometry.
All right, Bill, that's all the time we have for questions. Do you have any last thoughts?
No, well, thank you for having me. And, harmonizing radar and communication systems, of course, is very important to me. I did, just kind of as a final pitch, you'll have these all these materials, but there is a paper I put together in the IEEE Aerospace and Electronic Systems Society magazine, and it discusses why radar needs spectrum and how it uses spectrum and the trades that can be made. And this is a result of my participation in the American Midband Initiative, which I'm sure some of you in the room were part of that as well. So you might find that interesting. But thanks for your attention, and you should have the material to look at on your own. And if you have any questions, you certainly can email me, and I'll try to answer your queries as best I can. So thank you.
Thank you, Bill. And speaking of which, if you wouldn't mind checking the chat, just given the logistics here, we weren't able to monitor chat while we were streaming. So if you have access to that and there's some questions there, appreciate your engagement at that.
Okay, unfortunately, I lost the chat when I got cut off on Wi-Fi. So if anyone has, has that in text form, they could send it to me. I could send responses back to Mike. I think that's you talking, Mike, and then you can send them out.
All right, I'll get that message across. Thank you so much, Bill. Help me thank Bill for his
Okay,
presentation.
thank you. Have a good day.